Okay, so let's welcome Fanny Augeri from University of City Paris for the final talk of the day. And she's going to talk about large deviations of the largest eigenvalue of supercritical sparse Wigner matrices.
Okay, I would like first to thank the organizers for the invitation. It's a real pleasure to be here. So I'm going to talk about the large deviation of the top eigenvalue of sparse Wigner matrices. And this is a joint work in progress with Anirban and Basak. So in a sense, this talk will be the continuation of Kyung-Sik's talk that we just heard, and also Nick's talk that we heard yesterday. So our basic model will be the one of Wigner matrices. So this is a random symmetric matrix. And in this talk, this will mean that also the coefficients on and above the diagonal are all independent. And we will assume that the diagonal entries share the same distribution. And the same for the off-diagonal entries, but with potentially a different distribution. Okay, so you have two distributions, one for the diagonal entries and one for the off-diagonal entries. Now, we will make some moment assumption and some integrability assumptions. So we will assume that this matrix is centered and that the variance of the off-diagonal entries is equal to 1. Okay. And we will further assume that our matrix is sub-Gaussian in the sense that the log Laplace transform of the entries is at most quadratic. Okay, so you have two distributions. So two log Laplace transforms, lambda 1, 1 and lambda 1, 2. Now, if you take the supremum of a theta non-zero, then we will assume that this is finite. Okay, so Nick yesterday talked about the large deviations of the top eigenvalue of these Wigner matrices. And in this talk, we will consider a sparsified version of this model and ask ourselves, how does the sparsity affect the large deviation behavior of the top eigenvalue? So to this end, we will consider a matrix A, which is independent of W, which will be the adjacency matrix of an Anderson graph. So on n vertices and with parameter p, where p goes to 0 as n goes to infinity. Okay, so actually this Anderson graph, I will allow to have some loops. So I will assume that the entries on and above the diagonal are just Bernoulli P random variables, ID. Okay, and now I will form the matrix X, which is going to be the Hadamard product of W and A. So this means that we will multiply entry-wise W and A, and I will normalize this matrix by square root NP. Okay, so as Kyung-Sik mentioned in his talks, we can also see this matrix as the adjacency matrix of a network where you have these weights given by, you have the weight W on the Erdős-Rényi graph given by the matrix A. So note also that this normalization square root NP is made so that typically, I mean, the expectation of the L2 norm square of a row of this matrix is essentially 1, which you can interpret as saying that typically the degree of a vertex in this network is 1. Okay, so what can we say now about the typical behavior of the spectrum of these matrices? So in this talk, we will be interested in the sparsity regime where the mean degree goes to infinity. So we actually know that if you look at the empirical spectral distribution, you will still have the same behavior as in the dense case, meaning that this will converge weakly to the semi-circle law, which is a compactly supported measure on the interval -2, 2. But for the extreme eigenvalues, actually, you will have a crossover when the mean degree is about log n. And the reason of this is that at least when the weights are bounded, we know that the top eigenvalue is closely linked to the max degree in the network. So more precisely, so we know by the result of Tiromirov and Youssef. So if you assume the weights to be bounded, so we know that typically the top eigenvalue of X is asymptotically equal to a certain function of the maximum between 2 and the max degree in the network X. Okay, where actually, so lambda, this is an explicit function which is related to the Stieltjes transform of the sum isocolor. So it's d over square root minus d. Sorry, d over square root d minus 1. And the max degree here is just the maximum of the L2 down square of the rows of the matrix. Okay, but now one can check that because the tail distribution of a degree of a vertex decreases as exponential minus np, this result will give you actually the existence of a threshold C star, such that if np is above C star log n, then the top eigenvalue will stick to the support of the sum isocolor, so it will converge to 2. And if you are below this threshold, then you will see an outlier, okay, which is exactly given by this function lambda of the maximum degree in the network. Okay, so in general, you can also prove, if you have sub-Gaussian weights, that as long as the mean degree is much bigger than log n, then the top eigenvalue sticks to the support of the sum isocolor. Okay, and now you can ask the question, what is the large deviation behavior of the top eigenvalue in this sparsity regime, which is essentially complements the sparsity regime, which was considered by Koenig. So what is known in the sparsity regime is due to a combination of the work of Cook and Dembo on the one hand, and Bhattacharya and Ganguly. So they showed a large deviation result, not for the top eigenvalue of this sparse Wigner matrix, but of the recentered adjacency matrix, which is a related but slightly different model. So they proved that if the mean degree is much greater than square root n, okay, and you are looking at deviations which are delta np, and this is much greater than square root n, but at most of the order of np, then the tail distribution, so the probability that the top eigenvalue of A underscore is greater than delta np, this decreases as minus delta square over 2 n square p square log 1 over p. So in the first work, Cook and Dembo actually found a variational representation of this tail distribution. And later, this variational problem was actually solved by Bhattacharya and Ganguly, and this together gives this explicit formula for the asymptotic of the tail distribution. What is also interesting to note for our discussion is that this result also tells you that the optimal large deviation strategy is actually to plant a clique of size delta NP. Okay, so you can quickly check that actually this cost corresponds to planting a clique of that size in the graph. Okay, so but this result actually tells you something about the very large deviations of the top eigenvalue, which is then very far from the typical value of the top eigenvalue of A bar, because it's supposed to be of the order of square root NP. So now with Anirban and Basak, we actually proved for these sparse Wigner matrices the following result. So we computed the large deviation upper tail of the top eigenvalue. So for any t which is greater than 2, we showed that the tail distribution actually decreases as exponential minus NP times a certain function I of t, which I will describe now. Okay. So before that, I will actually need to introduce some notations and to make some assumptions. So we actually need to make a technical assumption, which is that the weights are sub-Gaussian in a stronger sense than what I actually stated at the beginning. So I won't go too much into the details, but essentially we need to have some sub-Gaussian concentration for convex Lipschitz functions of W. Okay, so this is a technical assumption which restricts the possible distributions for our large deviation result. But in particular, it's satisfied when the weights are bounded, or if the weights have strictly log concave distributions in particular. Okay, so now to describe the rate function, I will need to introduce some notations. Okay, so I will actually assume further that if you look at the log Laplace transform of a diagonal entry, you divide this by theta square, then this has a limit when theta goes to plus infinity, and this limit is equal to, this limit I will denote it by alpha over 2, which is something which can also be 0. For example, if you have bounded weights, or if you have or the distribution is lighter than Gaussian. So I will also assume the same for the off-diagonal entries. And here I will also make an assumption which is a bit more debatable, which is that this limit is actually greater than the same thing if theta goes to minus infinity, or more precisely than greater than the Lipsu when theta goes to minus infinity. So actually, this is just saying that the right tail of an off-diagonal entry is heavier than the left tail. So this assumption actually allows us to solve eventually the variational problem, which is associated to this large deviation upper tail event. And we can maybe discuss later more about it, but that's indeed easier in the analysis to assume such a thing. So further, I will introduce a function L, which is the expectation of exponential theta W1 square minus 1, and HL, the Lejeune transform of L. Okay, so maybe as you can guess, actually HL is nothing but the rate function of a degree of a vertex in the network X. Okay, if you look at the degree of the vertex I, this is nothing but 1 over NP, the sum of Wij square Aij, for j equals to 1 to n and j different than I. Okay, so you can quickly check actually that, so this is a sum of ID random variables, and its large deviation rate function is given by this function HL. Okay, so now with this notation, I will define two cost functions. So I will have a first cost function k of t, which will be 1 over 4 beta m of t squared. And we'll define another cost function j, which is defined as follow. So j of t will be the infimum of r squared over 2 alpha plus HL of s, with the constraint that r plus mt of s is equal to t, and r is positive and s is greater than 1. Where here, so m of t is just the Stiegler's transform of the semi-circular. So it's an explicit function. And now the rate function I of t actually is just the minimum of these two costs, k of t and j of t. So as our rate function is given in terms of a minimum of two costs, actually this is related to the fact that there are two competing scenarios in the large deviation event of the top eigenvalue. And these two scenarios are also reminiscent of what happens when the mean degree is constant. So you have a first scenario, which consists in planting a clique of a size which is diverging with n, but not too fast. So of size k, which is much smaller than square root np over log 1 over p. Okay, so this means actually that creating this clique has a negligible cost at the exponential scale np, because for each edges that you will have in your clique, you will pay log 1 over p. So if k is much smaller than square root np over log 1 over p, then you're not going to pay for having this clique in your graph. Okay, and on that clique, we will have weights which are of order square root np. Now, next to this scenario, there is another competing scenario, which is to have a high degree vertex with a high weight. So this first scenario has a cost which is k of t. Okay, and the second scenario, so the weights are also of order square root np. And the second scenario has a cost which is j of t. Okay, so here you need to find a compromise between the high weight that you put on the large weight that you put on the vertex and the degree of that vertex, which is S. Okay, so let me make some further comments about the rate function. So interestingly, the rate function that we obtain is always discontinuous. Okay, because you can actually check that I of 2 is strictly positive. Okay, so actually, so it's easy for K, that K of 2 is positive because M of 2 is 1. And here you see that in order to make this function vanish, you need to take actually R, which is 0, and S, which is equal to 1, the typical value of a degree in the network X. But then you see that you won't match this constraint for T equals 2. So actually, I of 2 is always strictly positive. So this means that you have the following picture for the rate function of the top eigenvalue at the large deviation speed NP. So the rate function should vanish at the typical value, which is 2. Okay. At the left of 2, you have the rate function is actually infinite because you have a change of speed. This was mentioned previously. And at the right of 2, you have then this function I of t, okay, which has then a right limit at 2, which is strictly positive. Okay, and we can also further say that I of t, this behaves when t goes to infinity quadratically, at least if alpha, at least if the max, I mean, yeah, at least if alpha or beta is positive. Yeah. Okay, and actually, so the fact that the rate function that we obtain is discontinuous is related to the fact that the large deviations are generated by finite rank perturbations. And we know that for the extreme eigenvalues of finite rank perturbations, you have a certain transition phenomenon that I will describe later. And this is somewhat transpire in this discontinuity of the rate function. Okay, some further remarks. So when you have light tails, so when alpha and beta are 0, you can also make sense of these cost functions. And actually, the rate function simplifies a lot. And the rate function I of c is just HL of t over M of t. Okay, so you don't actually have this scenario of a clique with high weights. You only have the high degree vertex scenario. So in general, we actually don't know how many transitions there are between these two scenarios. But we do know that when alpha is 0, then there can be at most one transition from the high degree vertex to the clique scenario. Okay, so if at all there should be at most one transition when alpha is 0. So it might be that you only have the clique construction, which is always winning, but at most you will only have one transition. Okay, so now in the remaining time, I would like to give some ideas about the proof. And I will start with the lower bound. So in this kind of large deviation problem, the lower bound is much easier to prove than the upper bound. So as I said, the large deviation of the top eigenvalue are actually generated by finite rank perturbations. And the extreme eigenvalues of finite rank perturbations are given by a certain transition. I mean, they undergo a certain transition, which is called the BBP transition, after Baik, Benarou-Péché. So what is this BBP transition? So if you take P, which is a finite rank matrix, and you assume that the top eigenvalue is theta. Now, if you look at the deformed matrix X plus P, so since P is a finite rank, you're not going to change very much the asymptotic of the global asymptotic of the spectrum. You will still converge to the semicircular, but you might deform the edges of the spectrum. And it turns out that if theta is less than 1, then the top eigenvalue of X plus P will still converge to 2. And if theta is greater than 1, then the top eigenvalue will localize at 1 over theta plus theta. Okay, which is something that I can actually rewrite in terms of the Stieltjes transform of the semicircular as the inverse of the Stieltjes transform at 1 over theta. So what is really striking is that it doesn't suffice that P has a positive eigenvalue to actually deform the edge of the spectrum. P really have to put some effort to, namely to have an eigenvalue which is strictly greater than 1 to actually see a deformation of the edge. Okay, so now let's see how we can use this transition in order to create a large deviation lower bound for the top eigenvalue. And we will do this with the first scenario, which is to plant a clique on the first k vertices, where k is going to infinity, but much lower than square root np over log 1 over p. Okay, and I will assume that the weight that I have on that clique, so the wij, I will assume that they are of the order of y over k times square root np, so very large weights. Okay, now if I work on this event, I can actually decompose my matrix by setting aside the principal submatrix of size k. So I can write it as some other matrix x hat plus a rank 1 matrix, which has 0 entries except for the principal matrix of size k. And here I have actually all the coefficients, which are y over k. Okay, remember x is the Adama product of A and W divided by square root of P. Okay, so now on this event, so I can decompose a matrix in this as a perturbed Wigner matrix. And what is the BBP transition telling me is that if y is actually strictly greater than 1, then the top eigenvalue of x is going to localize at a value which depends on y, which is n minus 1 at 1 over y. Okay, now let's see what is the cost of this event. By the cost, I mean the log probability of this event when you divide by NP. So since we chose the size of the clique to be much smaller than square root NP over log 1 over P, you're not going to pay for creating the clique here. You will only pay for moving the weights to having very large weights. So for the off-diagonal entries, you will have then 2 choose k entries. The cost of having one entry, which is of order y over k square root n p, this is y square over 2 beta k square. And the same for the diagonal entries, but this time you only have k of them. So you see that when k goes to infinity, you get the cost y square over 4 beta. So now if you want to create a deviation of the top eigenvalue around some value t, you see that you will have to choose y, which is 1 over m of t. And you get indeed the cost function k of t, which was in the stated rate function. So I guess it vanished. So maybe I will keep this board here. So this corresponds to the cost k of t. So for the second scenario, when you have a high degree vertex, you can also do the same argument, except then you will have a rank 2 perturbation instead of a rank 1 perturbation. But you can essentially do the same, and you will obtain this rate function as well. You will obtain the cost function j of t. Okay, so now we'll move to the upper bound, which is the most difficult part in this work. And I will try to sketch it in the case where the weights are bounded. So actually in our approach, the case of unbounded weights builds upon the case where the weights are bounded. And in that case, the approach is a bit more straightforward. So I will only sketch this part. So because we have a sparse model, we expect that it behaves kind of like heavy tail distributions. And therefore, we expect actually to see some localization phenomenon, which is going to be captured by the fact that the top eigenvector is going to localize somewhere. In particular, it's going to localize on these high degree vertices. So we will take U top to be a top eigenvector of the matrix X. And we will choose a threshold epsilon and look at where this top eigenvector actually localizes. So where it's put, where the entries are at least epsilon. Okay, since my top eigenvector is of unit norm, actually we know that the cardinal of J is less or equal than epsilon minus 2. So this means that you will only have a polynomial number of choices for this set J. But now, since we assume that NP is much greater than log n, this means that actually J carries no entropy. In the sense that you can essentially consider that J is a deterministic set. Okay, you can fix J, take unit bounds, because its cardinal is at most epsilon minus 2. You can do that. So that's actually a very nice thing, because now we can decompose the space according to this set of vertices where the top eigenvector localizes. Okay, so we will actually decompose X into a block matrix. Okay, where X subscript J is the J by J matrix, submatrix of X, and the same for the other 4 blocks. And I will do the same also for the top eigenvector. So I will decompose the top eigenvector into a very short vector v top and a delocalized part. Okay, so what is important to note is that so W top by construction is a delocalized vector in the sense that its L infinity norm is at most epsilon. Okay. So now we will just write the eigenvalue eigenvector equation. What we can do maybe first is that actually here, because the weights are bounded and J is a set which is of size of order 1, we can completely this matrix here is essentially negligible, so you can replace it by 0. So now if you look at the eigenvalue eigenvector equation, so you will get the following equations. What you can do is that if you assume that the top eigenvalue of X sits above the spectrum of this matrix, this submatrix X superscript J, then you can actually extract the delocalized part from the second equation. So you can actually write W top in terms of the resolvent of this X superscript J. Okay, you can do that. And now if you replace it in the first equation and you take the inner product with V top, you will obtain a certain equation, which will be the starting point of our large deviation analysis. So you will obtain the following equation. So the resolvent of X superscript J, if you take the dot product with Y V top and Y V top there, then this is equal to the top eigenvalue times the L2 norm square of the localized part of the top eigenvector. So far we did not use much from our model, but we are going to take this equation and try to extract a relationship between the top eigenvalue and the maximum degree in the network X. So now imagine that we could prove, and the difficult point is to prove actually at the large deviation scale. So imagine that we could prove at the large deviation scale that on the one hand, you really have localization of the top eigenvector in the sense that this V top carries a non-trivial part of the mass of the top eigenvector. And secondly, that this function, if you look at it formally as a function of xj, of X superscript J, this actually concentrates, or at least is upper bounded by its expectation up to a small error. So its expectation is actually, so the series transform at the top eigenvalue lambda x times the L2 norm square of Y V top. Okay, if you take formally the expectation with respect to X superscript J, this is what you would get asymptotically. Now, if you have proven these two statements, actually you are in a very good position to obtain the large deviation upper tail of the top eigenvalue. So indeed, now, so you can replace this inequality, which is here. So you can replace it here, and then you will obtain that the top eigenvalue of x divided by m of x, m of lambda x, sorry, this is less or equal than the operator norm square of y plus an error depending on delta. Okay, so you will get such an inequality. And here now you are essentially done because y is a very tall matrix. So y only has a finite number of columns. And it's actually not difficult to show that with high probability, the operator norm square of y is dominated by the maximum degree. Okay, and this amounts just to say that if you have a sparse graph and you take a finite number of vertices, then with high probability, their neighborhood won't overlap. So you can actually then deduce that the square of the operator norm of y is indeed bounded by the maximum degree in the graph. And then this allows you to get then an inequality between the maximum degree and the top eigenvalue, or at least a certain function of the top eigenvalue. So now you see that actually, upon a large deviation of the top eigenvalue, this will induce a large deviation of the maximum degree, and you are only reduced then to understand the large deviation of the maximum degree. And this is very easy to actually find. And this has a rate function, which is HL. So once you reach this inequality, you are essentially done. Okay, so the way actually we prove that you can indeed make these statements at the large deviation scale is by using some concentration argument. So this is clearly a concentration argument here that you have in this second statement. For the first statement, it's a bit less clear, but actually this is induced. This is implied by the fact that if you look at delocalized vectors, d epsilon, so d epsilon is going to be the set of vectors which have L infinity norm, which is less than epsilon. Now, if you look at the inner product of W x W, this cannot exceed its typical value, which is 2 plus little o. Okay, if you know that actually at the large deviation scale, you cannot have a high value of this inner product if you take delocalized vector, then this will induce that upon a large deviation of the top eigenvalue, the top eigenvector should localize. So if one looks closer at actually these two statements, you will see then that these are concentration statements, at least formally for the second one. Because you have obviously issues with dependence between VTOP and XJ. These concentration statements, they actually involve functions which have a specific structure. So these functions are all convex. But more importantly, they have a rank 1 gradient or subgradient, which is of the form W transpose, where W is a delocalized vector. So meaning that its L infinity norm is smaller than epsilon. So what can you say in general about the concentration of functions of this type? Well, very generally, we know by Lagrange, but it can also be derived from an inequality of Marton. So you know that if you take a function f on the set of symmetric matrices of size n, which is convex, and one Lipschitz with respect to the Frobenius norm, then it will have a sub-Gaussian concentration. So the probability that f of x is at least of distance t from its expectation, this decreases as exponential minus np t square divided by some numerical constant c times r square, where r is the bound that you have on the weights. Okay, so that's a very general concentration inequality, and a priori it's not, it doesn't go in our direction, because essentially it's saying that the large deviations of such functions have a speed which is np. So essentially they are at the same level as a large deviation of the top eigenvalue. So a priori you're not gaining anything. But actually here, this is a very general statement, and this overlooks something. So indeed, so this is very general, but actually f of x could concentrate much better. And the reason is that the structure of its gradients is special. So actually, so in the course of our work, we prove a improved sub-Gaussian concentration inequality for such functions. So we actually prove some kind of super concentration statement, which says that, so if you have functions with where the gradient spans in this kind of set, so of the form W transpose with L infinity norm of W, which is smaller than epsilon, then you can actually improve the sub-Gaussian, the variance factor in this sub-Gaussian inequality by epsilon square. And this is how we actually prove that at the large deviation scale, we can actually assume these two things, and in the end obtain the large deviations of the top eigenvalue. Okay, so that's essentially the proof. Now, to conclude, I will make further remarks on our statements. So I did not mention, but actually we can also say something about the conditional measure in the case where the weights are bounded. So we can say that upon a large deviation of the top eigenvalue, then with probability going to 1 as n goes to infinity, there exists a vertex with a high degree in the network X, which is above T over M of T minus some small error delta. So essentially what we are proving is a exponential equivalent between the top eigenvalue and a certain function of the maximum degree. And this function, without surprises, is actually related to the one which was in Tihomirov and Youssef result. So this is the inverse of the function that was in the statement. Another comment is that we can also obtain the large deviation upper tail for the top eigenvalue of the recentered adjacency matrix. Okay, so if you take A minus its expectation, you look at the top eigenvalue. Our method actually apply also for that model. And furthermore, we can also obtain the large deviation of the second largest eigenvalue of an Erdős-Rényi graph but with a restriction on the mean degree, which is that the mean degree should grow at least polynomially fast. Okay, so this was all I wanted to present, and I thank you for your attention.
Time for questions.
No, so we did not look at the heavier tail case, but I suspect that this is even easier, I guess, to analyze. So because in this case, you know, the degree of a vertex, I think the large deviation of the degree of a vertex are even easier to understand. So yeah, we haven't looked at that case, but I think that's natural question, I guess. Yeah, I would suspect that then actually, as in your results, you don't have you cannot have arbitrary large clicks. On your results, you only have clicks which have a bounded size essentially. And I think here it will also be the case. You will only have maybe 2 clicks. So just have a high weight on an edge, or having a high weight on a vertex, and that would be the dominant large deviation strategy.
Yep. Any other questions?
About the consequences of the large deviation principle on others, do you have, like for example, for when you are on your large deviation event, other consequences on the spectrum? So maybe on this event, the second eigenvalue, largest eigenvalue is also large, or something like this, or the eigenvector is the top eigenvector behaves in a certain way.
Right. So the top eigenvector, yeah. So it will localize. So in the case of bounded weights, it will have entries of order 1 precisely on the high degree vertex. Yeah, we cannot precisely compute what is the weight of the L2 norm of the localized part, but it cannot be arbitrarily large. That's all we can see from the equations. But yeah, it's about a delicate question, and well, I think we could extract maybe more informations. At least in the bounded case, I think we could extract much more informations from looking at, you know, I mean, here, I mean, okay, I already removed the YV top, but we could extract more informations so that, you know, if you are not well, yeah, we only show that actually the top eigenvector should localize, but yeah, we don't have more precise statements so far.
Okay, and for the other eigenvalues, so typically they are of order, the second one is of order T or much smaller. Do you move just one eigenvalue, or what's happening?
I would imagine that you have alone the top eigenvalue, which is large. I would imagine that typically the second one is of typical order.
Typical. Is of order 2. Okay. Thanks.
Yeah.
Anyone else? Okay, if not, then let's thank the speaker.